is power and efficiency. This is just vocabulary, basically. Learning what those two words mean and how to use them. Power is the rate of change of work. How do we write that symbolically? Well, they actually use P for power. You'll be happy to know. Power is equal to du dt. Where it makes way too much sense. We know that du is equal to F dotted with dr. That was our definition of work. The change in work is F dot dr. Okay, so if I want to make this into power, I just have to divide both sides by dt. So my dt goes over here, and I end up with power is equal to F dotted with dr dt. What's dr dt? Velocity. Good. So that's just equal to force dotted with velocity. If you dot your force with your velocity vector, you get power. Our units in SI, we would have joules per second. Does anybody know what a joule per second is? A watt. Very good. We use watt, which is the same thing as a Newton meter per second. That's what a joule is, a Newton meter. And then in AES, what do we use for power? Yeah, horsepower. But do we ever use horsepower in an equation? No, never, ever, ever. Because the AES system is stupid, and horsepower doesn't work in an equation without, making conversions. So what do we use in our equations? Foot-pounds per second. Good. So power would be foot-pounds, pounds per second. And then we use the conversion, 1 horsepower is equal to 550 foot-pounds per second. So immediately, if you're given horsepower, you convert to foot-pounds per second. If you end with foot-pounds per second, you convert back to horsepower. Yeah. Efficiency. Okay, so the last thing is efficiency. Efficiency is misused everywhere. The term efficiency is misused. It basically just means power output over power input. P out over P in. However, you know that power is also du dt, so you would see that the t's could cancel, so it can also be energy output over energy input. Most of the time, we use power output over power input, and it has to be less than 1. Anything more than 1, you have created a perpetual motion machine, and you will be rich, but you also are a liar, because it's impossible. So this example problem, okay, so we are given that this Jeep has a weight of 2,500 pounds, and it has a total power output of 100 horsepower. And we want to know, what is the maximum theta that it can climb at a constant velocity of 30 feet per second. First thing, we're going to draw a free body diagram because we need to compare directions. Now, if we had all these things in vector equation, we just use the dot product, but we don't. So we're going to have to do kind of a manual dot product with the angles that we're given. So we draw a free body diagram. We're going to have a normal force. We're going to have a weight pushing downwards. What else? What else is acting on this very weird military-style amphibious vehicle? Friction, good. Which way is friction pointing? This way. Friction is pushing the Jeep up the hill. But don't I always say that friction can't help? Yeah. How come friction's helping? Before it slips, exactly. That's basically what we're saying is that there's a moment being applied to these wheels, right? And that moment is trying to get the little particles of the tire that are hitting the road to slip. And friction is keeping that from slipping. So friction is pushing you up the hill. Is it helping? Well, it's getting you up the hill, but it's trying to keep those particles from slipping, which is really what the moment's trying to do. So in a way, it's fighting that slipping. It's just a beneficial fighting. Does that make sense? Kind of? Okay, so friction should be going that way. And we're going to tilt our coordinate axes just because it makes it a lot easier, x and y. On this one, I would say that I choose to tilt it because F and N are going to be benefited, but W's not. So 2 to 1, I'm going to go ahead and tilt it. And also because I get the sum of the forces in the y direction equal mass times acceleration in the y. And what is my acceleration in the y direction? 0, because of the way I tilted my axes. Good. So I can say my sum of the forces in the y, well, I'm going to have my normal force pointing up. And then I'm going to have to subtract the weight. So I have to figure out what that weight would be. I like to draw that separately. I got a weight pushing down like this. I got my x-axis and my y-axis. So I'd have a component in the y and a component in the x. And there's my right angle. I know this angle, theta. So I know that's going to be the same thing as this angle, theta. Okay, so I got all that. So n minus cosine theta, sorry. Theta. Okay, that didn't really give me a whole lot. I don't have a mu, right? So now what do I do? Well, I need that force, right? I need this F force here. So we have some of the forces in the x equals mass times acceleration in the x. And the thing I was missing is this little c down here with constant velocity of 30 feet per second. So that means acceleration in the x is also 0. And we get that frictional force minus 2,500 pounds times the sine of theta equals 0. So frictional force has to be 2,500 pounds times the sine of theta. And then we just do our dot product, which would be power is equal to F dotted with velocity, which would be 2,500 pounds sine theta dotted with, in the I, dotted with 30 feet per second in the I, which is 250 sine theta times 30. And that's going to be equal to R. So do I set that equal to 100? No, I have to figure out what it is foot-pounds per second. So we'd say 100 horsepower times 550 foot-pounds per second for 1 horsepower. Oops, I don't know what that was. And that's 55,000 foot-pounds per second is equal to 2,500 sine theta times 30. Theta is equal to 47.2 degrees.